here and, yeah. So if I'm walking in the negative direction and someone pushes me from behind, so it pushes me in the negative direction, well, my acceleration is negative because the force is in the negative direction. If I'm going in the negative direction and someone pushes me that way, which way is the direction of the force? Which way will be my acceleration? Let's go back to over here. Acceleration is the same sign as the total force. So if I'm being pushed in the positive direction, what is my acceleration?
Positive.
But if I'm going in the negative direction, I get pushed that way, well, I'm going to have to stop, and then I go back. So I'm going to slow down to start with, and then I will speed up as I start moving in the other direction. This way is also helpful if someone's at a stop. So I'm at a stoplight. The light is red. The light turns to green. Assume that I'm pointed in the positive direction, because I can make positive direction whatever I want, so I'm going to make it that direction I'm moving in. The light turns to green, put my foot on the accelerator, and the gas pedal, I should say, on the gas pedal, and I move. At that moment, I start at rest, and then I start to move in the positive direction. At that moment, what is my acceleration? Positive, negative, or zero?
Zero.
Why?
He's not moving.
All right, so let's think about that. Acceleration is the change in velocity over time. So if my acceleration is zero, that means my velocity does not change, which means I'm never leaving that stoplight. I think most of us have been at a stoplight before, but now you are here. So obviously that is not a critical condition. It is possible to move. Because acceleration is not dependent upon the velocity, it's dependent upon the change. If I go from 0 to something, my velocity changes. I should say 0 to something not 0. My velocity changes, therefore there is acceleration. So if your acceleration is a slightly different way. I'm assuming everyone here can drive, or at least has seen a driver. While you are driving, you have access to three things that physicists would call accelerators. What are the three things that cause acceleration while you are driving? Three things that directly cause acceleration while you're driving.
The gas pedal.
That's one that allows you to speed up,
The brake.
that allows you to slow down,
Steering.
and that allows you to change direction. Because acceleration depends upon the change in velocity, and velocity has a direction. I'm going to let this soak in for a little bit. Any questions up to here? I'm going to talk about sort of the scalar analogs and then get to the Usain Bolt example. Scalar analog. There's not really a scalar analog of position. Displacement, scalar analog is distance. The symbol for distance, delta x, delta y. Don't write the vector symbol. Scalar analog of velocity. I think I mentioned this earlier today. Speed. The symbol, just don't write the vector symbol, it's a V. V without a vector symbol is speed. Please don't use S. For distance, don't use D. And then I know I mentioned this one earlier. The scalar analog of acceleration is acceleration. You wanna take a wild shot at the symbol?
Okay.
Yeah, no vector symbol. Acceleration is the change in speed over the change in time. Velocity is the distance divided by time. Distance is just how far you went. So I'm starting in Columbia, South Carolina. I'm going to Winston-Salem. Let's assume it's 200 miles straight north. Good enough for what we're doing. I start in Columbia and I go straight there. I have the magic to be able to just go in a straight line. Well, if I can make it directly north, then yes, I have the magic to do this too. And let's say that I do it in 4 hours. What is my average speed? Or what is the distance I traveled? We'll start with that.
200 miles.
200 miles.
The time, 4 hours. What is my speed, average speed?
50 miles per hour.
Okay. Running. Go through this, please.
I'm sorry.
So 50 miles per hour. What was my displacement?
20 miles.
Are you stopping there? I have the coming from over there somewhere.
Is that all? I don't know.
What's he missing?
North.
Yes, it's a vector. Displacement in the vector column over here. Direction matters. 200 miles, and I shortened north to just n hat. What is my average velocity? Yeah, average velocity.
So 50 miles per hour north.
Yeah, there we go. Displacement divided by time. I got 200 miles north divided by 4 hours. I get 50 miles per hour north. So pretty straightforward. Now let's make it different. I start in Columbia, South Carolina. This time I'm going to take the scenic route. I start here and I take the scenic route and I go around, visit some various places, landmarks, and eventually end up in Winston-Salem. I looked at the odometer before I left. I looked at the odometer afterwards. And unlike the rental guy, I did the math correctly. And this is 500 miles. What is the distance traveled? 500 miles. What was my average velocity? I'm sorry, what was my average speed? Oh, I didn't tell you how much time it took. $10 hours. What was my average speed?
50 miles an hour.
Yeah, we must have been traveling really fast then. Don't do this when you're on the back roads. Especially in the speed traps. What was my displacement?
2 miles north.
It's the same as it was before. Displacement doesn't care about what you did in between. It just cares about where you ended up relative to where you started. But not dumb to be. What was my average velocity?
per hour north.
Ooh.
South? South, since you're going from, wait, no, never mind.
Think about the math definition right here. Displacement divided by time.
Between mile an hour north.
Yep. I ended up 20 miles, 200 miles north of where I started, and it took me 10 hours to get there. This is 20 miles per hour north. So now I'm racing Usain Bolt. We're going around a 400-meter track. There's the start and finish. Start and finish. 400 meters around. He does it in, I think I said 30 seconds before. So this is the time for Usain Bolt. And the time for me is 200 seconds. So we go all the way around the track. When he finishes, what is his displacement?
400 meters.
Not 400 meters.
0.
Yeah. He ended up exactly where he started. He is exactly at a starting point. So Usain Bolt's displacement when finished, at finish, is 0 meters. Now, it's supposed to be a vector on the right-hand side. Where I wrote down 0 meters, it is supposed to be a vector. But what direction you do if something with no magnitude, and you have what's called a zero vector, so you just put a vector symbol over the 0. What was his average velocity? Some of you are just afraid to say it because you don't believe it.
13.3 meters per second.
Say it again?
13.
No.
Oh, my bad.
You forgot what the average velocity. Go back over here. Yeah. In 30 seconds, he went nowhere. After 200 seconds, I make it across the finish line. What's my displacement?
0.
And what's my average velocity?
0.
I'm as fast as Usain Bolt. Then we up that. When he finishes, I'm here. Yeah, we'll assume I'm fast enough to do that. So when he finishes, there's my displacement. Is my displacement 0 when he finishes?
No. No.
Is my average velocity 0 when he finishes?
No.
I am faster than Usain Bolt. It just took some physics, didn't have to do any hard work, just had to know some physics, and I could be faster than he is. Now, some of you are looking at that and thinking, there's no way you're faster than Usain Bolt, I don't care how you want to spin it. Well, I did spin it correctly, however, most people, when you're talking about racing, you look at speed, you don't look at velocity, for a reason. Now we get into his average speed was indeed much greater than mine, because he went 400 meters in 30 seconds, which was 13.3 something, repeating, meters per second, whereas my average speed, so this is Usain Bolt, is 400 meters in 200 seconds, or 2 meters per second, which is not as fast as I walk. Probably if I ran at top speed, I would collapse at some point and just have to rest there for a while, so it probably wouldn't work out, something like that. All right, so 15 minutes. part that I usually do next usually takes longer than 15 minutes. All right, I'm gonna do things out of order here. I'm gonna make a note that I'm doing this out of order. We are done at 3:20, right?
Yes.
Okay. I got this backwards, that's lab, and this is class. I do an extension of the plus minus zero with some other situations, and that's gonna wait till next time, after the quiz. So instead, what we're gonna do is we're gonna derive the cake formulas. Because there's a relationship as sort of written out here by, about these. So I have velocity is the change in position over the change in time. And acceleration is the change in velocity over the change in time. Not happy with either of those. So, if I start out going 5 meters per second and then end up going 7 meters per second, what's my change in velocity?
2 meters per second.
Yeah. How'd you get that?
7 minus 5.
If I start out going 5 meters per second and end up going negative 7 meters per second, what's my change in velocity?
Negative 12 meters per second.
Okay. So change is always this minus that's final minus initial. So this is final velocity minus initial velocity divided by time. So that's equal to acceleration over 1. Got to cross multiply here, so I have final velocity minus initial velocity times 1 is equal to acceleration times time, or change in time. I'm just going to add final initial velocity to the other side over here. So I have final velocity is equal to initial velocity plus acceleration times time. Now, there was an assumption that I made when I started this. I said acceleration was the change in velocity over the change in time. But that's the formula for average acceleration. So I didn't really distinguish there between average acceleration and acceleration at any particular moment, because the assumption that I made, but didn't actually state, was that I'm assuming constant acceleration. So my average and instantaneous values are the same. And what we have here is the first of the cake formulas, which stands for constant acceleration kinematic equations. To my knowledge, I'm the only person who ever calls them the cake equations, but I find it very convenient just to call them cake equations. Now we have a nice little formula right here. Let's just do a little plug and chug, and then I'll talk about the variations of the way it's written. So if I go from 5 meters per second to negative 7 meters per second in 4 seconds, what's my acceleration? Well, negative 7 is equal to 5 plus acceleration times 4. So I'm just plugging in my quantities here. And acceleration ends up being negative 3 meters per second squared. We could check that easily enough, because acceleration is -3 meters per second squared, which is -3 meters per second, which means my velocity changes -3 meters per second every second. So if I look at my time and velocity, seconds and meters per second, I start out at 0 seconds. I say it takes place over 4 seconds. I start out going 5 meters per second. Well, after 1 second, my velocity is changed by -3, so this is 2. After another second, it's changed by another -3, so it's -1, -4, -7, which is exactly where I would expect to be at 4 seconds. Questions to hear? Now, other variations of the exact same formula. Oh, is that a question?
No.
Okay. If we take the next assumption that the problem starts when time is equal to 0, because remember delta t is just final time minus initial time. Well, if the initial time is 0, so we start the clock at the beginning of the problem, then this is equal to final time. And since I have only one time here, why bother writing? Why not just write time? So you can also see that equation as VF equals VI plus AT, which is generally it's the way I usually write it. But just recognize this T right here represents how much time the problem took place. Another variation of the way it's written is that instead of subscript I for initial, they use an O for original or a 0 for when time is 0. So you might see VF equals VO plus AT. And the other bit is we start the problem, we start out going 5 meters per second, we accelerate at -3 meters per second squared, and we just happen to be finding the time at 4 seconds, but at 5 seconds I've just put in a different value for time. So sometimes this F right here is just not bothered written, it's just the velocity at that time. So this is the velocity is equal to V naught or VI plus AT or delta T. So all of these variations, whether you use delta T or T, whether you use V sub I or V sub O or V sub F and just V, they all mean the same thing. And different textbooks do it differently, and I cannot keep it straight which one does which. This is the way that I usually write it. Let's go to the next step. Suppose I have a velocity time graph here. And I'm looking at velocity time graph looks like that. In other words, I'm getting faster in the positive direction as time goes on. This is some initial time and some final time. This is some initial velocity and this is some final velocity. So that distance right there, that's just the change in velocity. Whatever that is minus that, so this is my change in velocity. Going from here to here, going from this initial time to final time, well, that distance right there is just change in time. So my slope, and the symbol I use for slope, the downward sign. My slope is rise over run, that hasn't changed, so my rise is delta V. My run is delta T. That formula looks familiar. What is that?
Acceleration.
Yeah. So the slope of my velocity time graph is acceleration. Important enough to write down. Slope of velocity versus time equals acceleration. So if my velocity time, try that again. If my acceleration is constant, that's the same thing as saying my slope is constant, which says my velocity time graph is a straight line. If it is a straight line, my average velocity, well, that's going to be smack dab in the middle. My average velocity is whatever the average of VI and VF is. So if acceleration is constant, my average velocity, which we know is the displacement divided by time, is also equal to just my initial velocity plus my final velocity divided by 2. Multiply both sides by time, and we get VI plus VF divided by 2 times time. And we have the second cake formula with the same variations, whether it's delta T or T or VI or VO or VF, or just drop the F. There are 4 cake formulas. I'm not going to get to all 4 today. Some textbooks will put 5 in there, and I can't remember if it's yours or the calculus-based book which does all 5. I tend just to use 4 of them. The 5th one's just gravy. It probably means I should drive it because who doesn't like gravy? But it's unnecessary. I guess it all depends on what you're putting gravy on. There's some things gravy shouldn't go on. Ice cream, for one. So deriving the 5th one would be like putting gravy on ice cream. And on that note, enjoy your long weekend or extra working or whatever you're doing. Don't forget Monday is a school holiday. But we're not meeting then anyway. And none of your other classes count. Yes?
Do we print off our labs for Tuesday?
Oh, yes, please print out the lab for Tuesday. Thank you for reminding me. If you have printer issues, please let me know, but have I posted the first lab yet? Have you looked?
I'm not sure.
Okay. It should be dealt with by the weekend. If you go on the Blackboard, there should be a tab for labs or tab or something on the side that says labs. You click on that, there should be a lab showing with next Tuesday date or somewhere close in case I make a mistake. And you print that out. If you have issues with printing, just let me know.
So we don't have any homework for like chapter 1? Like, is there like homework for each chapter that we?
Then, yeah, if you go under coursework, under chapter 1, there should be a document which says something like textbook homework problems, something like that. Maybe even chapter 1 textbook homework problems. Open up that document. Those are the problems upon which the quiz is based.
But nothing to like turn in or?
No, the master sets will be handed in, but nothing for chapter 1. So long farewell, Avita Zane, good night. To you, and you, and you, and you, and you. Pardon? No, you can, there, if you go open up the syllabus, there's a link to where you get the PDF.
Oh, okay, appreciate it.
Yep.
Thank you, have a good one.
Yeah, you do.
Yeah, I'd signed up for your class before Christmas, and they said it was full.
Oh, yeah, there was,
And I emailed her